We'll proceed in vector field area, and then we will continue in proving the Green's theorem for dependent vector field. And then we will take some examples. So that is the idea. Okay, so concept is that we will proceed in the vector field. We will proceed in the kind of vector field. Okay, so we will proceed in the vector field, and then we will see that how we can kind of we can prove the Green's theorem for path dependent uh, vector field, and then we will take some example. So Green's theorem is kind of milestone in the vector field. Milestone in the vector field because it does the calculation through differentiation. I believe that people would like the concept of differentiation rather than integration. So integration is something that people think as antiderivative. Means derivative everyone enjoys, especially the chain rule. Through chain rule, you can find any derivative. Keep decreasing the complexity, and then you get the differentiation. I would suggest that people should suggest something in integration that is kind of analogous to the differentiation chain rule. There is chain rule in integration also, but sometimes it really keeps making the chain. So it is not that it is keep producing the way the differentiation does. So opposite someone should invent, discover, or whatsoever. Now what we have seen gradient field, vector field. So what we know by now, what we know, if I have if I have a x-axis, okay, I have x-axis, and then I have vertical along x-axis, then vertical equation is k, means k is the height, then k into the x-axis wherever I want. If I do, then it calculates the area of a rectangle. That is integration of k. This is what people told. If I have a height and then I have a width I call it x-axis, then width is from 0 to x and height is k, then area of rectangle is k into x. Okay, so this is something that is normal, but through calculus way, it is called that integral of k along x-axis from limit 0 to x is kx. If I have x-axis, there is 2.0 and x. I have a height that is k. Then what is height into x? That is kx. That is nothing but k spanning from 0 to x and making a rectangle. That rectangle area is kx. But if you talk in calculus term, then people would say that integral of k, there is a function called k, y equal to k, function over x is k. If there is a algebraic function k, then integral of k along x-axis is kx. If that is true, then setting the limit from 0 to x would result in kx. That is integration. Or if I want integration from 0 to a, their area is Ka. Integral of algebraic equation K along x-axis is Kx. Now setting this limit from 0 to x, 0 to a results in K. This is integration. So integration is nothing but finding the area. Finding the area is nothing but doing the addition. In a way that suppose that person, I always give this example. Or suppose person is collecting K orange per hour. Somehow he is getting K orange per hour. Then how much orange he is collecting at the end of A hour? That is K into A. K plus K plus K plus K into A oranges he is collecting. So one way is K plus K plus K plus K A times, or K into A multiplication, or third way is you draw a rectangle whose height is K and width is A and get the area of the rectangle. Third way is integration. Integration is nothing but calculating the addition with calculating the area, where it has its own terminology. So height, the distance along the width of the rectangle is nothing but width of the rectangle. If I talk in width and height rather than width and length, the width of the rectangle is independent component, that is x-axis, and height is dependent component, that is y-axis. Height is function over x-axis. Since the collection is constant, that is k, then fx equal to k. If fx is equal to k, then integration of fx along x-axis, that will result in fx dx. Whatever integration comes, limit from 0 to a, or first limit to second limit. How much is the orange collection between second day and 10th day? Okay, so first day and then second day. Second day to 10th day, 9-day collection is there. Okay, 2 to 2 to 10, 2 to 10. Okay, or in if I say 2 to 10, I believe it will come as 8. So 8 days collection, whatever, understandable. So 8 days collection. Okay, rather than 0, we are saying from 2 onwards up till 10. Okay, if that is the case, then 10 days collection only. Now if it is K oranges collection per day, then if I draw a graph of where the now independent component is x and dependent component is function over x, that is y. So in integration term, the function over independent component, that is fx dx, dx shows that integration is happening along which axis? X axis. Fx dx, nothing more than that. And then whatever the integration of fx comes along x axis, then lower limit to higher limit. Same thing calculating the area. More refined terminology. I would say kind of some kind of glassy way, means shining way of saying the addition. If I say that this is the k oranges per hour someone is collecting, at the end of a hour how much is collected, k into a, or area. But integration is not like function over. If I consider how many hours, then hour is independent component, that is x-axis, and function over x-axis is y-axis, that is fx. So if you want to calculate the area fx from lower limit to higher limit, lower limit is suppose a and higher limit is b, then fx dx, dx means along which axis? Fx dx, whatever the integration comes, means whatever the area comes, area will maybe in algebraic equation again. Set it from A to B. This is integration way of talking, same. If that is the case, then it would result in Kx, setting A to B would result in Kb minus Ka. Or if A is 0, then Kb. Okay, so this is something that is behind the integration. Now, consider that I have x-axis. Now, instead of this algebraic equation, okay, earlier I had algebraic equation k, I can have algebraic equation as kx. If it is kx, then instead of flat line over x-axis, it is like this, because if x is 0, then height is 0, and height is growing like a triangle. Then what is the area of the triangle? If it is kx, then it is kx square by 2, because whatever the area triangle is making, that is half of the rectangle it would make. Or if I take parallelogram way, then if this is the triangle line, then if I make a parallelogram, then again height by the width. So same thing. So height, then what is the height and what is the width divided by 2 or something like that. This is what I believe so. So this is the concept of kind of the area and integration. So if I take a rectangle, if this is a triangle, then this is area of triangle, then it is half of the area of rectangle it would make. If that is true, then it is x square by 2. So kx square by 2. Anyway, so this is algebra. I won't go more in it. So if it is x-axis and this is a function is something like I said kx or k or any polynomial, then what is the area if it forms a rectangle or any shape from A to B? This area, full area, that is fx dx integration from A to B. This proves that I am calculating integration along x-axis if it comes as dx. What about if I have x-axis and there is a vector field? Vector field is nothing but if I say algebra, then at each x, fx is changing. That is algebra. But vector field at each x, there is a vector. At another x, there is another vector. There is another x, another vector. This proves that the vector is nothing but equation over algebra. That's why it is changing with x. So if vector is changing over independent component x, then it is vector field. So vector field denoted by capital F, where algebraic equation is denoted by small f. So vector field capital F. Now if I want vector field, if this is the vector field at any moment, so it is algebra over, please watch the previous video. So it is algebra over it is a vector over algebra. So it has x component, since it is a vector, it has x component, y component, z component, and so on and so on. If that is true, then x component is function over xyz, y component is function over xyz, and z component is function over xyz, because these three components are again changing. If it is function over only one variable t, then it is parametric vector. Otherwise, it is a vector field. If it is a vector field, then if I want to calculate this vector field integration along this axis, then first I have to find this vector field's effective vector along this axis. This vector strength, how much it shows along this axis. I don't want this, I don't want perpendicular. I want what is the component of this vector along this axis. If that is true, then vector field dot product with the I vector, whatever comes, that will come as an algebra. That algebra dx, because I want along dx. So first make the vector field to behave in a way I want. So vector field dot with, dot means cos theta. So vector field dot with x axis or where along whatever I want the integration, and then whatever comes as algebra, that algebra will behave as a height, and that algebra dx. So vector field f dot I vector, I is unit vector along x axis, dx. If I take I inside it, then it becomes f, capital F dot dx vector. Now if I want to know this vector field integration along any axis u, x axis, y axis, any axis u, this is directional integration, then vector field f dot du vector. Okay, so if du vector at any point along the du vector, now since u is a vector, it can be vector field also. If it is vector field, then u may not be a straight line, it would be some curve. That is called line curve. So vector field is a vector field and this is also vector field. So vector field's integration along another line. So sometimes it is referred as line integral of a vector field. Vector field line integral. If that is the case, whatever it is. vector field f dot du. Du is also variation in algebra, and vector field f is also variation in algebra. But if it is u, then at any point of the u, I can denote it as a position vector, that is xi plus yj. So vector field f, again it has components f1, f2, f3, like that. So if I say vector field f dot du vector, then it is f1i plus f2j d of xi plus yj. If I do d of xi plus yj, it becomes dxi plus dyj. Now, if I do dot product, then I have to calculate integration along this line from point A to B, that is the integration from A to B, f1 dx plus f2 dy. So, this is the kind of line integral of a vector field, and that results in an algebra. F1 is an algebra, f2 is an algebra, f1 dx, f2 dy. Okay, now if the line integral capital F dot du vector, if line integral whatever if we have calculated, that results in a small f function, algebraic function, that is called potential equation. Okay, that is called potential function. The end result is small f. If I calculate the gradient of a small f, df by dx, df by dy, ij, then it would result in capital F. This is what is seen. If that is the case, then capital F, then small f, what we are calculating, it is dependent only on capital F, not on the in the path. So if it is something like this, then F, capital F, through capital F, I can also get the small f. If it is capital F and small f are only dependent of each other, not the path u, then I can get the small f potential function from the capital F, that is vector field. If I am able to get it, then it is called path independent. Path independent means to get the small f, I don't need u. Only through capital F I can calculate the small f, that is the net integral. If that is true, then capital F is called path independent. If that is true, then from capital F I get the small f, or capital F dot du I get the same f, small f I am going to get. So this small f potential function, I can just kick out capital F dot du and place the small f there. Now f, small f, algebraic equation limit from a to b. That is the new integration. So small f just set a and b. This proves that if capital F vector, which has a potential function of small f, generated from vector field itself, then it is path independent. Net integration is path independent. Depends upon the beginning point and end point. If beginning point and end point is same, and then we are calculating the line integral over a vector field, where vector field is path independent, then it would result in integration of 0. So line integral of a vector path independent vector field for a closed loop, because beginning and end, it depends upon beginning end and end only, whatever the potential function is. If integration of capital F dot du vector results in potential function f, and then I set a to b and a to b are same a to a, it will result in 0 only. So for path independent vector field, the in a closed loop, the line integration is 0. Okay, these are two things that we saw. Third thing is that if I have a vector field capital F, that is equal to capital F1i plus capital F2j, then F1 equal to, so full line integral, if it results in a small f and capital F have component F1i plus F2j, then capital F1 equal to d, small f potential function, df by dx, and F2 equal to df by dy. If that is true, then d2 f by dx dy and d2f by dy dx are same. D potential function small f. Okay, gradient of small f is capital F. Then df small f, df by dx is first component of the capital F, that is f1. So f1 equal to df by dx small f, and f2 equal to df by dy. If that is true, if that is true, then df by dx, if I differentiate with y, then d2f by dx dy, and this another one, df by dy, it differentiate with x, then d2f by dy dx. dy dx or dx dy, they are nothing but showing the direction of xy plane. dy is y-axis, dx is x-axis, then dy dx or dx dy is xy plane. So both are same. If both are same, then df2 by dx and df1 capital F, df1 df2 by dx and df1 by dy, they are also the same. So for path independent case, df2 by dx minus df1 by dy equal to 0. Okay, they are the same. Why they are the same? Because I said that f1 f1 I plus f2 j capital equal to potential function df by dx I plus df by dy j. If that is the relationship, then f1 equal to df by dx, f2 equal to df by dy. If that is true, then f2 f df2 by dx is nothing but d2f by dy dx. df1 by dy is nothing but d2f by dx dy. Okay, if right hand side are same, then left hand side are also same. So path independence vector field d2f by dx minus d2 df1 by dy are same because they are the same. Okay, now Green's theorem is that if it is anyway, if it is path in, this is called curl test. It generates a curling in the sense that f2, which is y component, I am deriving with x, and f1, that is x component, I am deriving with y. So it is trying to do a curling. Okay, this is curling. Okay, y component, that I am checking how much y component's derivation. Okay, y component, how much it is changing. If I see the rate of change along y x axis and x component, how much vector field is changing if I see the change along y axis. So df2 by dx equal to df1 by dy when it is path dependent, or df2 by dx minus df1 by dy equal to 0, it is path independent. So closed loop integration, that is f1 dot du vector equal to df2 by dx minus df1 by dy equal to 0 for path independent. Consider that it is not, this is curl. So curl formula, if I want the curl formula is df2 by dy, df2 by dx, df2 by dx minus df1 by dy braces kx. Since it is in xy plane, I am doing curling. So the resultant vector is along the kx anyway. Now, if that is the case, now it shows the path independence, then what is the integration, line integration for the path dependent? If it is path dependent, then you have to calculate capital F dot du for each path. Or if it is a closed path, if it is a closed path, if it is a closed path, then you have, then if it is vector path dependent, then you have to calculate the, okay, if it is a rectangle, if it is a rectangle, then all four sections you have to calculate, the someone has to calculate the line integral for path dependent for all four paths separately and add it. This is path dependence. Okay, if it is path dependent, then you have to calculate for the all the section. But if it is closed loop, like rectangle is a closed loop, circle is a closed loop, If it is a closed loop, then there is any easy way to calculate the path independent, path dependent in line integral. Then Mr. Green come into the picture and he is saying that if it is path independent, then vector f dot du is same as df2 by dx minus df1 by dy. Then, then, then if they are same because they are zero, then again they are same for the path dependent also as far as integration is concerned. This is what Mr. Green is saying. So now for path dependent, if I want to calculate line integral over a closed loop, then it is again f dot du, where u is the line curve along which I am calculating the line integral. But here it is df2 by dy minus df1 by dx. Okay, what would be the integration for it? Okay, so he is saying the integration for it is along dx and dy. The integral sign we keep it along which axis? df2 by dy minus df1 by df2 by dx minus df1 by dy. We understand that this integration we have to do if this results in an algebraic equation. Then this integration we can do, but along which axis? Then he is saying along xy plane. If it is xy plane, then I have to integrate with dx dy. Then if it is xy plane, then I have to put two integrations. One limit in xy x-axis and another limit in y-axis. This is what he is saying. So as per the Green's theorem, if you have a closed loop, means it creates a region. If there is a closed loop, rectangle starts from here and it forms a closed loop, then there is a region. If there is a region in the closed loop, then if I calculate, if I have a vector field capital F which has component F1 and F2, then df2 by dx minus df1 by dy, it results in an algebraic equation. That algebraic equation I have to do integration along the xy plane, that is dx dy, not full xy plane. Whatever it results again in algebraic equation, I have to set limit from in the region only, left side to right side in the x-axis, left side and right side in the y, to double integrate. Then it results in the line integral of a vector field along a line that is a closed loop. So what is the leeway? What is the leeway? What is the sigh of relief that Mr. Green is showing? df2 by dx differentiation minus df1 by dy difference. So the algebraic equation what it is carrying, it is coming one level low. So line integral is not through integration, it is through differentiation. One layer it is coming low. Then if I do dx, then it is easy now. Whatever integration comes, set the limit, it becomes constant. Okay, now only you have the term with the y that you do dy. Amazing. Okay, a person who carries, what he did is that whatever the complexity of integration is, that complexity he distributed in a region, rather than if complexity is happening because there is a line curve, then that complexity he distributed in two integrations, dx and dy. But it is far easy now. Okay, so Green sir, you are great. Means it is something what he thought is exemplary. Now, how someone can prove Green theorem? Let's take one rectangle because I need a closed loop. This may not be a perfect proof, but this is how it is found in the book and everywhere. Someone has to think perfectly. Anyway, so if I take a rectangle, then rectangle left side is A, right side is B along x-axis, and along y-axis it is C to D. That is the rectangle. Then if I want to calculate the line integral, then four sections I have to calculate separately. Let's calculate for this section. First horizontal section from A to B and y is C. If that is the case, then line integral, as we talked already, that if I have f capital F dot du, then du converted into xi plus yj, then dxi plus dyj, and f converted to f1i plus f2j. Net it becomes f1i f1 dx plus f2 dy. That is the integration. Now the y dy, y equation is c, is a constant, it's a rectangle. So dy is 0. So f2 term gone, only f1 term remained, f1 dx. So now integration of from a to b f1 dx is the line integral of the first line. Let's take another line, okay, above line. So there are four lines. Left corner is a comma c, another is b comma c, then b comma d, and a comma d. That is the line. So if I take the horizontal line first and then next horizontal line, then direction is like this. Mr. Green says that the line curve, the region, whatever the region we are calculating, the now the area integration, calculate the area, that area should fall left side of the boundary. Okay, so if I take from A to B, then C to D, then B to A. The next line is B to A. Now I have to calculate integration from B to A, and then again f1 dx plus f2 dy. So dy gone because equation of y is d gone. So f1 dx. Now f1 if I see, then it is variation of xy. Now I have two equations, two line, two integral. The first integral is f1 dx a to b. Another is f1 dx b to a. f1 is a function over x and y. What is x and y? f1 is x, okay? Then x is x because it is variation. For that I have to calculate the integration, where y is c, constant. So f x comma c. And next one f1 x comma d, because bottom line is y equal to c is the equation, that above line is y equal to d is the equation. So integral a to b f1 in braces x comma c dx plus b to a f1 bracket f1 bracket and then x comma d dx. Now if I do this, then b to a convert to a to b minus. Then it now integration is a to b f1 x comma c dx minus f1 x comma d dx. f1 x comma c dx minus f1 in bracket x comma d bracket dx. Okay, if that is true, then if I have f1 x comma c minus f1 x comma d dx, then internal it results in another integration where limit is from c to d, and the equation that I want to integrate is dfy dy. If I have dfy dy, if I want to integrate along dy, then it is nothing but integration, then it is nothing but full term. If I have f dash x, consider a algebraic function that is f, the differentiation of f is f dash x or df by dx. If I want to integrate f dash x along dx, then full would result in fx1. Okay, so if I have capital F1 x comma c minus capital F x comma d, then that would result in f dash in differentiation of x, differentiation of f fxy or whatever. F differentiation means f dash df d capital F1 by dy, that is a better term, d capital F1 by dy, integrating it with dy, that would result in that. So that would result, that is kind of if I have f1, okay, if I am saying there are two limit f1, consider in simple term. If I say small f b small f in the bracket, small fb minus small fa. Then it is nothing but the f dash x dx, f dash x dx limit a to b, f dash differentiation, f dash x dx become fx. Now setting the limit a to b result in fb minus fa. Okay, so here if we calculate, the limit is from c to d, limit is from c to d, and here it results in f x. If I leave it, then f1c minus f1d. Okay, if it is something like that, then it is f dash 1, f1 dash means differentiation of f1 dy, integration of f1 dash dy from c to d. If it is something like that, then integration of f dash is df1 by dy. Now full terminology turned into double integration. One is from a to b and another is from c to d. Inside is df1 by dy and then integration with dy. If I do from left side to right side, I did two horizontal. If I did do for two vertical, they would now result in same. Here it is a to b and c to d. There it would result in c to d and a to b and then f2 by dx. If I take all together, because I have to add everything, so the I am talking about c to d and a to b and f2, okay, c to d and a to b. Okay, if that is the case, then that is df2 by dx. Okay, now this proves that both, if I go with pen and paper, then one will be negative. There is a switching in the sign. So if I add all together, then it would result in a c to d, a to b, and then df2 by dy minus df2 by dx minus df1 by dy dx dy. Okay, so that is the case. I believe it is clear. So I'll reiterate. So if I calculate the first line integral of horizontal line bottom and line integral of horizontal line top, two line integral. Line integral of horizontal is from a to b, f1 dx, f1 dx. Top is b to a, f1 dx. If I add these two, then it results in a to b, f1 dx minus f1 dx. First f1 is nothing but function over x and c. Another is function over x and d. So capital F x comma c minus capital F1 x comma c minus capital F x comma d dx. Now leave the dx and leave the integral. Now it results in f1 x comma c minus f1 x comma d. This inside term can be represented as integral from c to d df1 by dy. Okay, if that is the case, then whole results in integration from a to b, c to d, df1 by dy dx. Same way, if I do this for two vertical, then they would result in again c to d, a to. So it is up to down. So well, I believe it will be negative. So minus a to b, c to d, and then f2 by dx dy. If I add all along, okay, if I add all along, then it will be a to b and c to d and df2 by df2 by dx. Take care of the sign. Df2 by dx minus df1 by dy dx dy. So this is the closed loop integration in a region. This is Green's theorem. So no need to think about the closed loop, just think about the region. So if you have xy region, then df2 by dx minus df1 by dy, that results in algebraic equation, and that you have to integrate with dx dy, that is xy plane, not full xy plane. Limit is on x-axis it is a to b and y-axis it is c to d. What is a to b? If it is a circle, then if it is origin, centered on the origin, then a to b is minus a radius to plus a radius, and then minus a radius to plus a radius along the y direction. So this is Green's theorem to calculate the path dependent vector field in a closed region. Region is always closed one. Means in a closed loop. No need to go for line integral full. This is easier way. Now consider vector field is y square I plus xj. Y square I plus xj. Okay, now this vector field I need to calculate along a region, that is x is from 0 to 3 and y is from 0 to 2. That is the reason. I believe it is a rectangular region. So from 0 to a, 0 to 2 is 0 to 2 is 0 to 3 is along x-axis and 0 to 2 along y-axis. The vector field is y square I plus xj. Now let's calculate the line integral with the Green's theorem. Green's theorem said dy df2 by dx. So f2 is x, so it results in 1 minus df1 by dy. f1 is y square, then it results in 2y. So 1 minus 2y is the algebraic equation dx dy. So dx, if I integrate, it comes in x minus y square x. If that is the okay, I believe it is 2y, x 1 minus 2y. So x minus 2xy is the integration. So if I set limit from 0 to 3, then it will come in x minus 2xy. So 3 minus 6y. 3 minus 6y. Now 3 minus 6y, y is again in polynomial of power 1 1. Now integration is easy. Now it will come as 3y minus 6y square by 2. Set limit, okay. So it will come as 3y. 3y minus, it was uh, I believe it was 6y. So 6y square by 2. So 3y square. 3y minus 3y square. I believe so. If I set it 2, then it becomes 6 minus 12, I believe. Or it will come as 6. Okay, something like this. Okay, now it is far easy. Once you differentiate y square and x, it comes as 1 minus 2y. Now if you integrate with x, then it becomes x minus x y square. Just set the scalar limit, then it comes in 1, then if it is 0 to 3, then it comes in 3 minus kind of 3 minus 3y, 1 minus 2y, then 3 minus 6y. 3 minus 6y, that came at the end. Now if I integrate with the y, then 3y minus 6y square by 2. So 3 minus 3y square. Now set the limit and you get the result. So quickly. So for dependent, path dependent vector field for a particular region, then it is so easy. Okay. Now we talked about curl testing. df2 by dx minus df1 by dy. If I calculate, if it is 0, then it is path independent. If it is not 0, then it is path dependent. If that is the case, then what about we had taken example? Let's see this only. Y square I plus xj. This vector is path independent or not. If that is the case, then df2 by dx is 1, whereas df1 by dy is 2y. 1 is not equal to 2y. So this is path dependent. Another example is 2xyi plus xyj. This is what we had taken, 2xyi plus xyj. This is path dependent or path independent. Now if I do, the f2 is xy, so df2 by dy is x, and df1 by dx is df2 by dx is 2xyi plus xyj. f2 is xy, df2 by dx is y, whereas f1 is 2xy. So df1 by dy is 2x. So 1, 2x, 2x, and here y. Y is not equal to 2x. So it is path dependent. Path dependent. Okay, we had taken another example as y cos x. I believe so. So y cos x plus y plus sin x. Y cos x, okay, plus y cos x I plus y sin x j. This is what I think we had taken. So if that is the case, then the f2 component is y plus sin x. If I differentiate with x, it becomes cos x. And now f1 component is y cos x. If I differentiate with y, it becomes cos x. Cos x equal to cos x. So this is path independent. So this is about the Green's theory and curl mechanism. So what is in 3 dimension about the curl equation? We saw that if I have df2 by dy minus df2 by dx minus df1 by dx, df2 by dx minus df1 by dy, if that is the algebraic equation, then if I calculate in vector, that is k vector, you can go in k direction. This is for 2D. What about 3D? Then for 3D, the curl vector, it is called curl vector, df2 by dx minus df1 by dy in k axis, along k axis, that is curl vector. If I calculate in algebraic fashion, that is curl test. Curl vector in 3D is now df3 by dy minus df2 by dz in I direction plus okay, df2 by dx minus df1 by dy in k direction. Okay, now similarly df1 by dz minus df3 by dx in j direction. So this is curl vector for 3D. We will talk more on vector field as far as 3D is concerned, that how we can change into parametric equation. Idea is how we can solve 3D vector field. That is a kind of little complex topic, and see how far we can go in this direction. So this is Green's theorem to calculate the line integral in a loop, in a region, in a closed region, in a closed loop, closed region with df2 by dx with curl vector. So that we saw. Okay, we will proceed now in the 3D area. So that we will see.